Hello everyone, and welcome to another ICTS virtual string seminar. We are happy to have Upamanyu Moitra from TIFR with us today, and he's going to tell us about near-extremal fluid mechanics. Over to you, Upamanyu.
Thank you very much, Vishal. And let me begin by registering my thanks to the organizers for inviting me to give this talk. This is truly an honor for me to speak at ICTS today. And so a very good afternoon to you all, and good evening or good morning wherever you are. So what I'm going to talk about today is near-extremal fluid mechanics. This is based on this recent paper that I wrote with my advisor, Professor Sandeep Trivedi, and my fellow graduate student, Sunil Sake. I guess both of whom are here today. And this paper came out a few months back. And this is going to be mostly very basic talk for some of you, and I hope there are a lot of questions, and I'll be happy to answer questions as we go along. And so without further ado, let me just go ahead. So the fluid gravity correspondence basically states that uh, Einstein gravity in asymptotically anti-de Sitter spacetime in d+1 dimensions is equivalent to nonlinear fluid dynamics in d spacetime dimensions. To be more precise, it asserts that the Einstein equations of gravity map directly to the nonlinear equations of fluid dynamics, which are also known as Navier-Stokes equations. And this has been a remarkable discovery at the turn of this century. And here are some key references in this regard. And these are all very influential papers that shaped the understanding of fluid dynamics and its connections to gravity. There were some earlier works with respect to linearized hydrodynamics and fluid dynamics that goes back to the work of Polycastro, Sons, Tarinis et al. But our starting point would be this series of papers, and most importantly, the last two papers were the two of the papers where fluid dynamics was explored in cases where the fluid system was dual to uh, a charged black hole. And obviously, many of the authors are here today, and I apologize in advance if I make some incorrect statements, and I hope I'll be corrected by them as we go along. So let me now give an introduction and explain briefly the setup of our calculations. So our aim is to investigate fluid dynamics for nearly extremal black holes and branes. What do I mean by nearly extremal black holes and branes? So we are looking at systems which have a temperature and a chemical potential. And we are looking at situations in which the temperature is much smaller than the chemical potential. This is what we mean by near extremal. Conventional fluid dynamics, as was expounded on the series of beautiful papers, and there are many follow-ups that I had shown before, that would explore this situation in which the fractional rate of variation of various fluid parameters is the smallest scale in the problem. Namely, let this hash stand for some parameters of the fluid, namely the chemical potential or temperature or the fluid velocity. Then with respect to the directions along the fluid and that which also includes time, uh, the fractional derivatives would scale like the omega, which is the frequency, and k, which is the spatial momentum. And conventional fluid mechanics would explore it in the limit where this fractional rate of variation is the smallest scale in the problem, smaller than temperature. And because we are interested in near extremal systems, that would also mean that the temperature is smaller than the chemical potential. However, in the work that I'm going to describe now, we would be interested in the so-called unconventional limit, where the local temperature is the smallest scale in the problem. Namely, the temperature will be smaller than the fractional rate of variation, and which in turn will be smaller than the chemical potential. So this is the regime of parameter space that we are interested in exploring now. So our setup is one of the simplest setups in which there's a temperature and chemical potential in gravity, and which is also dual to a fluid system. This is the Reisner-Nordstrom ADS black brane in 4 dimensions. The metric here is given in this form, which is the Schwarzschild-like gauge, where this R square FR is the FR function is given by this, and near the horizon the FR goes to 0. The gauge potential is of this form. The mu is the chemical potential. The Q is the charge density carried by the black hole. M is the mass density. And just to be clear, in this talk, I will have set the ADS length scale to 1 throughout. So there might be some cases where you find that the dimensions are not what you expect. Then the dimensions are to be supplanted by appropriate factors of this LADS to make sense. So what is the extremal limit? The extremal limit is the case where this function FR has a double zero. And what does that mean? That means that the black hole will have a zero temperature in the extremal limit. And then it will also have a, as I said, a double zero. And in this case, the near horizon geometry of the near extremal black hole at a fixed chemical potential will look something like this. So let me spend a few more words on it. So this is the chemical potential, and the chemical potential depends on the charge density and the radius of the horizon. However, we are interested in treating the system in a way so that the chemical potential is kept fixed and the temperature is slowly varied, and we see what that gives us. This in particular means that the chemical potential is fixed at its extremal value. And then if you just do the maths, you will find that the metric takes something of this form, where within dots is the same factor that appears here, just as in Schwarzschild gauge. And you might be puzzled by the appearance of this T here, but no, it's the T. If you don't see the T over here, it simply is an artifact of the fact that we are at a constant chemical potential. The important thing to notice is that this part of the geometry is ADS2, and the geometry factorizes in 2 parts, and this other part just goes away and it becomes a factor of R2. So this is our basic setup. Now, just to get going, we will walk throughout in some coordinate system called the ingoing Eddington-Finkelstein coordinates, which is defined by this quantity V, and this which is t plus r star, where r star is the Ricci-Wheeler or tortoise coordinate defined by this integral. Just to say, the black hole horizon is mapped to minus infinity in the r star coordinate, and the asymptotic boundary, which is at r equals infinity, gets mapped to r star to 0. And in this coordinate system, the metric assumes the following form. There's a dv square and there's a cross term dv dr. The dx square and dy square part remain as they were before. And the gauge potential is transformed to dv from dt. So you might ask, what's the use of this coordinate system and what's so great about it? The answer is that the coordinate system is regular on the future event horizon. If you remember, I said that on the event horizon, this function fr goes to 0. Now you can easily see that even if this goes to 0, because there are off-diagonal components of the metric remains perfectly regular on the future event horizon. And furthermore, this coordinate system gives us a convenient way to describe the fluid gravity correspondence. So here's a picture of the geometry. Hello? Yeah.
Can I ask a question here?
Yeah, sure.
The vector potential in your gauge vanishes at the horizon. Is this how mu and q are related?
Yes.
Okay, thank you.
Yeah, okay, great, thank you. Yeah, so this is a rough picture of the geometry. This is the black hole horizon at RH plus T, where T is temperature. So let me make a parenthetical comment here that this T here is not the actual Hawking temperature, and it's just a rescale version of the Hawking temperature with some factor of 2 pi over 3, so that the horizon lies somewhere nice, namely at RH plus T. This is the ADS2 region and this near horizon region. And then after some point, it just, the ADS2 region, the throat just opens up and goes up to the asymptotic infinity to the far horizon region. And here's a boundary of the ADS2 region, which we have erected at R equals RB. Now, let me make a comment about what this RB actually is. This RB is, let me emphasize, a completely fictitious surface, and there's no real existence of this surface. And this is something imaginary that we have erected to facilitate the computation, and it will become clear why this is important. The real surfaces are obviously the black hole horizon and the asymptotic infinity. But there are some features of this fictitious surface worth discussing. The fictitious surface is located at a region where it's still good enough to be called ADS2, which means that this RB minus RH is much smaller than RH itself. But it is far enough so that the effects of the finite temperature have died away. So the temperature is much smaller than RB minus RH. So this is our basic setup. And before I go on to the next section, I would like to pause and ask all of you if there are any questions.
So this RB makes the distinction between outer and inner region. Is this why you have introduced this?
Yes.
Okay.
Indeed.
And the answers will be independent of where this RB is. Right?
Precisely. Yes. You have anticipated the role of the RB, but this RB will be important because I mean, as we'll see that we'll do some sort of matched asymptotic expansions, and we will match some quantities near this RB. But ultimately in all physical quantities, the RB will drop out. Anything else? Okay. If not, then let me go forward with a prototype model. So this is a prototype for the fluid gravity correspondence. So we consider a minimally coupled massless scalar field as a prototype. So why do we choose it? Because this illustrates some key features for the actual gravitational and electromagnetic perturbations. And to those who know the language, this will correspond to exactly the tensor sector of the actual gravitational perturbations. If you don't know what that means, never mind. This is not important to the discussion at hand. And we will study this minimally coupled scalar equation here. And for the fluid gravity correspondence, what we do is we turn on a non-normalizable source term at the asymptotic infinity. And this is this source term at this phi naught e to the minus I omega v I kxx. And we study the response, response in the scalar field to turning on this source. And we take this omega and k to be slowly varying compared to the scale set by the chemical potential. So omega over mu and k over mu are both much smaller than mu itself, much smaller than 1, sorry. So this is the equation that we want to study. And far from the horizon, in the approximation that omega over mu is much smaller than 1, and this response itself is of order omega over mu, we get the dynamical equation, which is the same as that of conventional fluid dynamics. Namely, on the left-hand side here, we get an equation involving the response, which is this phi 1 out, and with just purely radial derivatives appearing here and no other spatial or time derivatives appearing. On the right-hand side is this omega, which appears as a source term, and this phi naught, which was turned on. And what we have to do is solve this equation. And this equation is very easy to solve. We can just write down the solution straight away. This phi 1 out can be written as the b1 out minus this integral, and there's another constant a1 out. And notice that this inner integral we choose to do from this surface RB to R prime. In this case, we could have well chosen the lower limit of the inner integral to be RH, but as it turns out, it will be more convenient for higher order calculations to do the calculations this way. So what's the behavior near asymptotic infinity? Phi 1 out has this behavior. This B1 out, which is a constant term, that's a non-normalizable part of the response. And this A1 out involving this 1 over R cube, this is a normalizable part. So since we demand that our solution should have no non-normalizable part, we will say that we'll set this B1 out to 0. But this still leaves this normalizable part, and this still leaves this constant A1 out, which we don't know nothing about, we don't know anything about, and which we have to fix by looking at the what the scalar field does sufficiently close to the horizon. So let us proceed with setting B1 out to 0 for now. So now what we do is we expand this solution in the vicinity of the horizon, having set this B1 out to 0. And let me say that for now, I am doing an expansion in the case where the temperature is strictly 0. So the black hole is perfectly extremal. So if we do that, if you will notice that this is 1 over FR and this has 1 over R minus RH square behavior here. So having integrated it, we get in a series in R minus RH, something that goes like 1 over R minus RH, then something that goes like log of R minus RH over RH, and both of which involve the unknown constant, the hitherto determined unknown constant over here. And then the dots indicate terms which are regular in R minus RH. So what happens in conventional fluid gravity correspondence is that we do get just one divergent term here, and then by setting the coefficient of that term to 0, we fix the constant once and for all. However, let us see what happens here. So if we say that let us remove the leading 1 over R minus R, is there a question? The leading 1 over R minus RH divergence. So we simply set this whole quantity to 0. Therefore, this A1 out becomes I omega phi naught RB square minus RH square. And the function, having gotten rid of this one, now behaves like a log of R minus RH over RH with a coefficient like this. So here's the apparent sign of trouble, that if we remove the leading divergence, I mean, I'm putting divergence in air quotes because we'll see that it's not a divergence, but I'm getting ahead of the story. By a choice of this constant above, there's a log divergence that remains. And if we continue this solution inward right down to the horizon, this one diverges. And one might be reasonably tempted to conclude that the correspondence breaks down and there's no hope of having a correspondence at low enough temperatures or at 0 temperature. So before we analyze the question further, let us ask why this happens.
Actually, I have two questions here.
Yeah, sure.
So first about 50. 50 is a constant, it's a number.
Yes.
50 is a number.
Yes.
And why is it allowed to do the expansion near R equal to RH? Because this is the outer region solution.
Yeah. So I'm actually I got ahead of the story by saying that this is an outer region, but I'm all I'm doing is that I'm not doing it very much near R minus RH. I'm doing it sufficiently close to the horizon to see what the behavior is. So I'm at the moment I'm just claiming that as treated purely as a mathematical function, this one diverges. I'm just making an expansion about R equals RH.
Okay. So maybe in the next slide you will match it with the inner solution or something.
Precisely.
Okay.
And you had another question?
No. So this 50 was the other question. Okay. 50 is a constant.
Oh, wait. So now the question is, what's wrong? What's wrong is that in case of extremal and near-extremal black holes, the inner region has an ADS2 factor, where time is more spatial than the boundary spatial coordinates. I mean, in other words, this has an emergent set of isometries near the ADS2 region. So the near horizon extremal geometry in the ingoing Eddington-Finkelstein coordinates for the extremal black hole looks something like this. And you will notice that the line element is invariant under a rescaling. And what is this rescaling? Where this time coordinate or the time-like coordinate v goes to lambda v and the r minus rh goes to 1 over lambda r minus rh. Under this scaling, you see that they transform oppositely. So this one remains same And this one also remains the same. So the point is that once we are sufficiently close to the horizon, by a suitable rescaling, we can never say that the frequency truly becomes small. The frequency can always be set to unity by some scaling transformation. And as a result, something that we had ignored in the previous analysis actually shouldn't have been ignored if we were careful enough. So we would have to include the effects of the non-zero frequency term to get the solution correctly. So here's the region. So we are doing something on the out, which I've already explained before. But on the inside, we have to take care of the non-zero frequency effect. And here is one more final identifying feature of the boundary surface. So I said that once it's close to the horizon, we cannot neglect the effect of frequency. But we can say that the frequency is smaller than this quantity RB minus RH, and imposing this additional condition will allow us to match the solution on the outside and inside near this matching surface R equals RB. Is that okay?
Actually, sorry, one question here. So, so this is that you have 0, 1, the expansion. What is the expansion parameter here? In the previous expansion parameter.
Oh, yeah, I'll come to the expansion parameter. So our basic expansion parameter is omega over mu. That's omega over mu and k over mu. But our as we see that this omega enters the story in two different ways. One associated with the rescaling of the radial coordinate, which we can scale away, and which has to do with the near horizon ADS to scaling symmetry. However, there's another factor of omega, and which is here, for example. This omega is related with the breaking of the scale symmetry, and this gives rise to a source term. And this omega, as we'll see, we cannot rescale away by a redefinition of our radial coordinate, because this corresponds to a breaking of that symmetry. So outside will always be expanding in omega over mu and k over mu, but inside near the horizon, not near the horizon, sorry, near the matching surface, we will also be expanding in omega over R minus RH or omega over RB minus RH. This guy over here. And that is for the purpose of matching. Is that okay?
Yeah. I understand. Since outside region, the expansion is in powers of omega.
Yes.
But the inside region, the powers of omega do not make sense. So you will.
I'll explain shortly. It will also make sense in a the powers of omega will also make sense. I mean, once you have gotten rid of all the omegas that are associated with the near horizon scaling symmetry, there will remain some omegas, and this is that epsilon, and we will do a perturbation in them. Is that okay?
Yes.
Great. So this is what the relevant differential equation should look like in the near horizon region. And now I have transformed to our R star coordinate, and you can see for yourself how that works out, and it's a very nice calculation. And the point is that in the inner region, we cannot neglect this term over here, which we had neglected earlier, anticipating that phi 1 in itself should be of order omega. Therefore, we had dropped this term on the outside, but on the inside, we have to keep it. And let me here emphasize the role of two different omegas. This omega over here comes because of this R star here. And if you just rescale the variable away, if you let's say rescale r star, you can get rid of the omega here, but there will be an omega that remains here. So even in the inner region, there's an omega over RH that remains, and it is this omega over mu that remains, and I'll be using RH synonymously with mu, and it is this omega that will be a perturbation parameter. And this omega directly doesn't have anything to do with the perturbation theory, but we'll see the role it plays. So this is the differential equation we are interested in solving. So we can solve it straight away. This has following forms. This has something called A1 in, something with B1 in e to the 2I omega r star, and something that comes purely from this term with a source where this function E1 is the exponential integral function, the properties of which would be there in many textbooks. So we want to impose now ingoing boundary conditions on the horizon, and we will have this exact solution. So by ingoing, we can get rid of this B1 term. So that leaves us with this one A1 in and this integral function. So the nice thing about it is that the whole function is finite towards the horizon. So if you remember, I said that r star goes to -infinity towards the horizon, and if you examine the properties of this function over here, you will see that this function actually drops to 0. So on the horizon, phi 1 in becomes A1 in, and if you expand it near the boundary of the ADS2 region, this R equals RB surface, you will see that there's no 1 over R minus RH factor at order omega, where the only factor is order omega. There will be some order omega square, but that's a different story. So therefore, we see that first of all, the divergent behavior, the apparently divergent behavior on the horizon is completely removed just because we included this term. Furthermore, if you just expand it for small omega r star, which is this region over here, you will see that there's a logarithmic term with the precise coefficient given exactly by this. So that's something nice. That's our first indication that we are doing something right. So I think it's good to pause at this point and ask if there are any more questions on what I've said so far.
Hello.
Yeah. Yes.
So can you just say more about what is the near horizon behavior in this case?
You mean this guy?
Yeah, in this exponential function expression.
Yes. Yeah, so I can tell you right away. So if you go far towards the horizon, this exponential integral function behaves like e to the minus 2I omega r star over omega r star. The two exponentials cancel, and there's a 1 over omega r star.
Okay.
And that because the r star goes to minus infinity on the horizon, this term just drops away.
So the point is that, like this is goes like order omega to the power 0, a constant of order omega to the power 0.
Yes.
It?
Yeah.
Okay.
Yeah.
And the statement is that, like so this is exact in omega. Is that
okay? There are two things to say. I mean, given this equation, this is exact in omega. What I'm not claiming is that this is not exact in omega to all orders, namely that we have not even included perturbations of higher order in omega over, let's say omega square over mu square. So in our epsilon counting, this is order epsilon. So to keeping epsilon fixed, this is exact in omega. But remember that this, so the appearance of the same omega is a little deceptive at times. But this exactness in omega has nothing to do with the exactness in omega, in the sense of you get an exact relation for all omega on the boundary field theory. No, it's not that. And I hope the point will be clearer when I discuss the higher order calculations next.
Okay.
Yeah. You had another question? Let me just go ahead then. So here's what I was saying. So this is the general strategy for our higher order calculations. So this is our epsilon, which I said earlier is just omega over mu or k over mu. And here's this some variable we call zeta, which is omega r star, which is just omega for the extremal case near the horizon, just becomes omega over r minus rh. And let me point out something interesting here. So this phi 1 in, so once we express it in the zeta variable, this is a function of zeta, this is also a function of zeta, but there's an omega remaining outside, this omega over mu. So this is exact in zeta, but this epsilon remains. So I think that's another way to answer your question, Loga, that it's exact in omega as far as the zeta dependence on omega is concerned, but not otherwise. So on the outside, which is, let's say, the region greater than RB, we get a standard perturbation theory expansion at order epsilon to the n. One of the constants, you remember these constants that I had shown earlier, it's fixed by normalizability on the asymptotic infinity. And the other, this A out, is left unfixed, which will be fixed by comparing the data near the horizon. So on the inside, we perform a perturbation theory in epsilon after having scaled out the omega dependence in this quantity xi. I'm sorry, this should read xi. Sorry, this should read zeta. And once we do the two expansions, or once we obtain the two solutions, we would match the functional forms of the inner and outer solutions near r equals rb, where now we will be working in some standard coordinate system with our with all our omegas in place. And as I said to a question earlier, this is essential to match the solution near the matching surface r equals rb. However, this rb, being a purely a fictitious quantity, drops out of all the final physical objects or physical observables. And the outer and inner orders can get mixed. I'm sure some of the comments above may seem mysterious, and which will be clear when I go to an explicit example, which is second order. So before I go there, is there any question?
Yeah, I have a quick question.
Yes.
If that's, yeah. So the metric that you considered in the first place was linearized in a sense that you took it up to linear order in T, if I'm not mistaken, right?
That's right. That's right. Yes.
And I mean, are you considering the metric to be fixed, but you're considering these fluctuations to be of higher orders, or
yes. No, yes,
okay.
That's a very good point. I probably should have emphasized this earlier. So for the scalar field case, I'm working in a fixed background where my metric is, where the near horizon metric is this, and the far horizon metric is precisely this. So this is a fixed background that I'm considering. And I'm considering the scalar field in this background because it illustrates some of the key features that we'll see emerges in the actual fluid dynamics case. So, so far I'm not discussing any gravitational or electromagnetic perturbations.
Yeah, but my concern is, like, when you're considering higher order perturbations, shouldn't the full consistent set of equations involve the second order corrections from the
Oh.
metric as well.
No. Okay, good. So what I'm considering is higher order perturbations in phi itself, where by higher order, what I mean is that the phi has an expansion in derivatives, and in terms of the perturbation parameter epsilon, we can just do it self-consistently without, I mean, it's just a test field. We are not taking the scalar field to back react on the metric, if that's what you are concerned
Okay,
about.
yes. That was okay. Thank you.
Yeah. We are just using a test field.
Okay, thank you.
Yeah, no problem. So things become more interesting at second order, and this is where we get the really interesting physics out. So now we completely have solved what phi1 out is. We have fixed our A1 out, we have fixed our B1 out, we have, and although I haven't shown it, the A1 in can also be fixed. Now this phi2 out, when we do the same thing again by inserting the phi1 out on the right hand side of the equations, we can get a solution. And here, if we now do the expansion of the outside solution near the ADS2 boundary, we get a behavior like this. So in phi2 out, there's omega square over RH, the log of R minus RH over R minus RH. Then there's a 1 over R minus RH. And then there's log square R minus RH. And here's something interesting to notice, that the sort of quote unquote most divergent term does not have any adjustable constant before it. So there's no way we can set this to 0 like we did earlier by demanding that, okay, we are setting the most divergent term to 0. So if you think that the correct thing to do would be to remove the leading divergence, that's definitely not doable. What we have to instead carry out is a systematic expansion. And now, if we look at phi1 in, remember that our phi1 in had this form. And what we now do is this omega, we keep as it is, and we expand this whole thing to linear order in omega near the ADS2 boundary. When we do that, we get a behavior like this on the outside. So on the, you see that the first terms, they just match up, which are highlighted in blue. This, sorry, is there a question? Sorry. So this RH, so the phi2 out and phi1 in, they have the same functional form with one crucial difference, and that makes things much more interesting. The scale of the log on the outside is set by RH, and the scale of the log on the inside is set by omega. And we have to match the 1 over R minus RH terms across this ADS2 boundary to determine what our A2 out is. So this involves this quantity F1, which depends on the boundary value of RB, which is not important for the matching at the moment. And this is what I meant when I said that the orders, they get mixed up when we do the inside and outside perturbations theory the way I described we do. So the phi1 in, which is our formally an ordered epsilon quantity, this gives rise to an ordered omega square, which matches with ordered omega square over mu square terms on phi2 out. And this is what keeps happening as we go to higher orders. So you might obviously ask me, what does phi2 in do? So using the perturbation theory, you can also calculate phi2 in, and phi2 in will definitely have order omega square factors, but that does not have any role in matching this solution and getting this A2 out right. Instead, the leading behavior from phi 2 in near the ADS2 boundary will be something like log square, which is not essential for matching now. Any questions yet? Great. So here's something interesting. So we match the coefficient of 1 over r minus rh to obtain what A2 out is. And we see, remember my earlier remark that because of the different scales of the logs in the two places, we get the A2 out to be order omega square log omega over RH plus some terms which are analytic. So the outer constant which appears in the normalizable part of phi is non-analytic in omega and therefore non-local in time. And this is a true issue because this A2 out will determine the expectation value of the scalar operator on the boundary theory. And if you take a Fourier transform of this quantity, you will get an integration kernel like t minus t prime to the minus 3 and not delta functions or derivatives thereof, which means that the quantity that we measure will be non-local in time. And at higher orders, there will be newer non-localities. And generically, the most non-analytic term will go something like this, epsilon to the n, log to the n minus 1 of omega over RH, plus terms which are sort of less non-analytic, if I may say so, plus obviously analytic terms which we do not worry about. Now, the interesting point to notice is that the perturbation theory here is well controlled in spite of the presence of higher order non-analyticities. For example, over here, if you just got this log of omega over RH, you would have thought, okay, we are dead. I mean, because as omega goes to 0, this just blows up. However, because of this omega square here, this is actually a small quantity for small omega. Therefore, at higher orders, we will get more factors of something like omega times log of omega over RH, which makes the perturbation theory well defined because it's smaller at each order. And we can also treat varying chemical potential and temperature and boosts in the adiabatic approximation in the same way. So I think it's another good point for me to pause and ask if there are any questions.
I have a question, more of a comment rather than a question.
Yeah, sure.
So when you say non-local in time, I guess what is happening here is that since the ADS2 throat is infinite, the perturbation is scattering from like near horizon ADS2 region and going to infinity. And since this throat is infinite, the scattering happen at many places, and that's why you are seeing the 1 over power law tail rather than the.
Indeed.
Is this a correct?
Yeah, I think so.
Actually, similar thing happens in flat space. In flat space at asymptotic infinity, you don't get power law tails. But I guess this is related because ADS2 times S2 is conformal to flat space. I think there is a relation between them.
I see. Yeah, I have not thought about that last point, but I think it's certainly true that this is closely tied to our ADS2 isometry. But I think what you say is interesting, and I think I'll surely look into it. Anything else?
Upamanyu, I just wanted to make sure that I understood you correctly.
Yeah.
So the statement is that first of all, this what you call as phi in.
Yes.
Is always phi in 1, phi in 2, and so on and so forth.
Yes.
So phi in k is something which goes like omega to the power k. Is that's your notation, right?
Yeah. No, actually, yeah. I mean, as I said, phi in. Yeah. I mean, it goes like omega to the k times a function of zeta.
Function of zeta. Yeah.
Yes.
The omega
Which
is
also
inside
involves
V.
omega.
Yeah, function of some omega r star. Okay.
Yes.
So it's some omega to the power. So phi in n will be something which goes like omega to the power n
Yes.
into some fn of omega r star.
Precisely.
Okay. And your claim is that, you know, like and all these guys go to some are finite as you take r to rh.
Yes.
Is that
Indeed. That's right.
okay? Okay. So okay, good.
Hmm.
So now, what is the log behavior of this when you expand it near RB of phi in n? Is there, because you probably did not say, but you said
I
that
think
phi
this will
in
be just
1,
log to the n.
it will
Something
go like
like
log to the power n. Okay.
Yeah.
Because you said phi in 1 gives you a log
Yes.
which matches against phi in 2,
Yes.
phi out 2, sorry.
Yes.
And so on. So so the statement is that phi in n will give you a log to the power n, which will match with phi out n plus 1. Is
Yes.
that
Yes. That's exactly what I think it will be like.
Okay. And the statement is that, so once that matching is done, you kind of forget about those terms.
Yeah.
Those terms are matched.
Yeah.
And the other terms, those terms are automatically matched without any constants.
Yes.
And the other terms, to match them, you fix the constants, and that gives you the expression that you have written here for A out n.
Yes.
That,
yes.
Okay, which is like epsilon to the power n, log to the power n minus 1.
Yes.
Okay.
Indeed.
Okay. How does the Fourier transform of this guy look like?
This guy?
Of A out n. So you said A out 2 goes like 1 over t cube, delta t cube. But how does A out n look like?
A out n will look like 1 over t to the n, t to the minus of n plus 1, or t to the minus n minus 1. And there will be some factors of log as well. In general.
Log t, you're saying?
Yeah, log t. I mean, in general, the kernel would go like something like log of t over t whole to the n. Okay. Or, I mean, I might be missing some one factor, n minus 1 and n minus 2. Those sorts of things could be there. But in general, yeah, that would be, that is what it would look like in Fourier space.
So you're saying that you get a tail which is same power series in 1 by t and log t. Is that?
Yes.
Is that the claim?
Yeah.
Okay. And that you could show to any order in n, is that?
Well, we have shown it explicitly up to the third order in our paper. I mean, as to how it works. I think it will be very straightforward to generalize it to higher orders, although I do not have a rigorous proof at the moment. But I think this is what the structure suggests that it will look like.
So the claim is that, you know, like you're able to show it till n equal to 3.
Yes. I mean, show it explicitly without any complications. Okay. Yeah, and I think there is an argument that you could do it, but okay, let me just remind myself of it and come back if I have the time later.
Okay. Okay.
Okay, yeah, let me go ahead then.
Actually, just one more comment here. Can I understand this from the Green function point of view? So in ADS2, in the near horizon region, ADS2 near horizon region, the Green function for the scalar operator will have a branch.
Hello, I'm sorry, you are getting cut off for some reason.
Sorry.
Hello, yeah, I can hear you now.
Can you hear me now?
Yeah, better.
Yeah, I am asking if this log omega behavior can be understood as a branch cut in the scalar Green function in the ADS2 region.
Yes, I think so. Yes. Yeah, I think also when we discussed some of the although it's not there in the talk today, it's true that for the extremal case, there's a branch cut in the Green function and a branch point at omega equals 0. And what we are seeing here is precisely a signature of this non-analytic behavior, and that's completely right.
Okay, okay, thank you, thank you.
No problem.
Does this also match the results from like Schwarzian 2-point function or something?
Sorry?
So does this match, for example, if you compute the thermal 2-point function in Schwarzian theory, would you get the same results?
Oh yeah, that's a great question, and I think it will, and it's something that we have to do, because I mean, we have also investigated a lot of the near ADS 2 physics in a couple of papers, and actually this is what was the motivation for studying this system in the first place, and I think it surely will, and although that remains to be worked out.
Okay, because this 1/t cubed is how the Schwarzian 2-point function behaves in when t is large.
Yeah, and in general, it has a it has some anomalous dimensions.
Okay, I see. Thanks.
Yeah. So now we go on straight to the finite temperature case, and in this case we get what I call the inner solution. Earlier we get to be this quantity, and this I1T in has this behavior. And here, to answer, I think something that came up in the discussion with Loga, it's more obvious that things are good towards the horizon, because as you go towards R minus to minus infinity, this is exponentially cut off by the temperature. And here you don't have to even appeal to some particular functions to see why this decays on the horizon. And as mentioned before, the effects of finite temperature die away near the boundary. However, they are very important near the horizon. There's an additional parameter in the interior region, which I'm calling T over omega. Actually, it will be a general parameter of our whole theory. And let me just state what it looks like. The function here, this I1 in. This I1 in has this behavior near the ADS2 boundary, where omega over R minus RH is small. And there's a log here which involves T, and then there's this function which is called a digamma function, which is a logarithmic derivative of the gamma function. So here's an important point, that on the outside, the fractional corrections are in T over mu for finite temperature case. And therefore, remember that we have already introduced our expansion parameter epsilon before, and T tilde. Whatever is T over mu is actually epsilon T tilde, because whatever is T over mu, we can write as T over omega times omega over mu, which is epsilon times T tilde. Therefore, because the T tilde is a small parameter, and if we are interested in only order epsilon parameters, the outside solution would be the same as that we get from the extremal solution, because the order T over mu corrections we can forget at order epsilon. However, even at this order, the interior solution would be significantly different. And just to state the new physics over here, at second order, there would be additional non-local terms. And earlier, we simply had something like omega square log of omega over RH. And now, in addition, we would have arbitrarily high powers of the number T over omega. And this is sort of bringing already some alarm bells, because there's omega in the denominator. And we would, if we just transform it back into the real space, we would get positive powers of T minus T prime in the integration kernel. However, that's not big an issue, because in that case, it will be cut off by the low temperature, because every power of T minus T prime will be accompanied by a power of the temperature capital T. So in this case too, the perturbation theory is well under control. And finally, there's something that needs to be mentioned, although I don't go into it here. There are also exponential small corrections in omega over t, and as always, we forget about exponentially small corrections. So these are the important lessons that we draw from here. We do the perturbation theory in two perturbative parameters. One is epsilon, which is generically omega over mu or k over mu, and t tilde, which is t over omega. Now, there's something that I would like to bring your attention to, that at first order in epsilon that I had shown earlier, there's no sign of non-locality on the outside. Remember that all the log that had appeared in A2 out, that appeared only at order 2, that's at second or higher orders. At first order in epsilon, there's no need to keep any finite temperature correction on the outside, and we can walk in the extremal limit itself. And this is very important for our actual story, which is simply fluid mechanics, and this will help us simplify some of the calculations. At higher orders, there are non-localities, but the perturbation theory is under control, and we get an asymptotic series. And similar results can be obtained for actual metric and gauge field perturbations, although some of it are considerably more complicated than what we have discussed here, and which I'll not go into in the interest of time. And because the physics point, I hope I have made clear. So I think this is a good point to pause and ask if there are any questions here.
Hello.
Yeah.
So maybe it's probably obvious from the way you presented it, but I just wanted to confirm.
Yeah.
So the claim is that this works in any dimension D?
Yes.
Okay.
Yes. Yes. Yeah. I mean, as long as you have some near horizon ADS2, it appears to be independent of the particular dimension that you have, or any other. But I mean, there should be some emergent ADS2 isometry in the problem.
Okay.
Actually, regarding this comment, in extremal BTZ, the wave equation is exactly solvable in terms of confluent hypergeometric functions. So can one test your perturbation expansion? You think I mean, the way you have organized this omega log omega, can one test this using the exact solutions for BTZ?
I see. Yeah, I did not know about the BTZ solution, but I think yes, that would be great. If I think it will surely be testable. Although, I don't know. I mean, at least if you come in the scalar field, then obviously it can be easily tested, I think. But there are no actual gravitational perturbations in BTZ, right?
No. I mean, you can design. You can consider the so-called massive Strominger's.
I see. Okay. I see. Yeah. I think that will be a fantastic place to test this idea. Thank you. I didn't. I hadn't thought about this.
Yes. Sorry. Can I just interrupt for a minute, Upamanyu?
Yeah. Sure. Please go ahead, sir.
No. Before Amitabh made the comment, I was about to say to Loga, the one case I'm not fully sure if there might be something additionally to think about is ADS3, just because the asymptotics are a little different and so on. But I think for ADS4 and above, it should work. And ADS3, because of boundary gravitons, etc. If there's something more to worry about, you all might know about whether there are additional things to worry about in fluid mechanics in ADS3. So that case I haven't thought about, but okay, it's very interesting. If there's an exact solution, we can certainly compare, as Amitabh says. I say this just because I haven't thought about ADS3 fluid mechanics so carefully. Okay.
Yeah, just to say that the fluid mechanics part, I don't know. I mean, what I know is that the scalar equation can be exactly solved. Okay. And once you solve the scalar equation exactly, one can try to set up an expansion of this type.
Right. Okay. Sure. No, that's a good comment.
Yeah. So thank you very much for the comment, and thank you to sir as well. So are there any other questions or comments? And or else I'll go on to presenting some of the results of the actual fluid dynamics. Okay, if not, then let me take a huge fast forward and just bypass all the technicalities that emerge in solving the coupled Einstein-Maxwell equations and all sorts of boundary conditions that we impose. So with this previous lesson in mind, we can construct the bulk solution in linearized perturbation theory to first order because of changes in some fluid parameters. And this allows us to construct the covariant stress tensor and charge current to the required order. So the curly E here is the energy density, the U mu and U nu, the three velocities. Mu is, as always, the chemical potential, and the sigma mu nu is the shear tensor, which is constructed out of derivative of the velocity field. This is the one derivative term. This is obviously the ideal fluid part. Then because there's a charge current as well, there's this rho u nu, which is the perfect fluid part, and then there are this one derivative parts which involves the acceleration field, which is sort of the time derivative of the velocity field, and derivatives of the chemical potential and the temperature and projected onto the direction orthogonal to the 4 velocity. And just to say that these are all kept to the required order, and this curly E and rho have to be kept to linear order in T for this to be a valid expression up to some particular order. So let us discuss some interesting physics here from the previous constitutive relations. Where we keep the T dependence carefully in the perfect.
Sorry.
Yeah, sorry.
I'm just trying to understand. So here there is no non-local.
Right. Because it's up to first order. Remember the lesson that I had drawn here, that at first order there's no non-locality on outside, and this is what rescues us. That all sorts of non-localities hit us only after second or higher orders.
So if I understand right, you're keeping like order to order epsilon and to order T tilde. Is
Yes.
that what you're doing?
Yes, exactly.
And you're ignoring anything of like which has an epsilon square or T tilde square or something.
Exactly. Yeah. Epsilon or epsilon square T tilde. Namely, I'm ignoring epsilon T terms. More precisely, in the constitutive relations over here, there are no T dependence here, because if we keep the T dependence here, that would be an order epsilon square T tilde term. And if we have to keep that, we also have to keep the non-local terms.
Okay. So are you keeping epsilon times T tilde?
Yes, epsilon times T tilde insofar as it's there in the this perfect fluid part. Because in perfect fluid part, we have to keep the leading temperature dependence, the first subleading temperature dependence, and that's just order T. Because it's simply order T, it's formally of order epsilon T tilde. So up to order epsilon T tilde, it's here.
So you're keeping order epsilon, order T tilde, and order epsilon T tilde.
Jim.
Yeah, and there's no purely order T tilde terms anywhere. I'm sorry.
Yeah.
Is that okay?
Okay. Yeah.
So now we can linearize these equations, and from the conservation equations, which is del mu T mu nu equals 0 and del nu J nu equals 0, we get some set of linearized perturbations, and solving them, we can deduce the dispersion relations for various modes of the fluid. So there's a transverse shear mode, there are a pair of longitudinal sound modes, and there's a longitudinal charge diffusion mode. And the interesting thing is that if you simply did conventional fluid dynamics, then you would also obtain some nice dispersion relations. And if you take the T going to 0 limit of those dispersion relations, you would end up with the same relations, the same quantities as I've shown here for the shear and sound modes. For the charge diffusion mode, this dispersion relation is off by a factor of 2 compared to conventional fluid mechanics. And there's a 2 in the denominator in the relation extrapolated from conventional fluid mechanics. Well, this is definitely not a disaster because, okay, we get what we get. And there's no telling the dispersion relation how to behave. But it turns out that in getting the earlier dispersion relation without the 2 in the denominator, there's a cancellation of temperature in getting the dispersion relation. In particular, what this also means is that an ordered epsilon t term, which is formally an ordered epsilon square t tilde term in the constitutive relation, this can change the dispersion relation by an order 1 factor. So therefore, for obtaining this dispersion relation, it's not reliable to keep only the terms we have kept here. Unfortunately, as I've remarked before in response to Luga's question, non-locality enters the general constitutive relations at the same order, particularly for the shear mode. So there's no way we can simply obtain the corrected constitutive relations without having to deal with the non-locality. Fortunately, however, in a particular setting when the variation of the energy is 0 and the variation of the fluid velocity is 0, we can solve the whole set of Einstein-Maxwell equations. And it just turns out that we get local terms in the constitutive relations, which are also of order epsilon t. And this happens because of some very nice cancellations, and our leading term itself is of order epsilon t in the various response functions. So along this trajectory of linearized perturbations, we get something which is a modified dispersion relation, which agrees with the conventional limit here. Therefore, in conclusion, we do get all the dispersion relations predicted by taking the 0 temperature limit of conventional fluid mechanics. Is there any question about these issues?
So what is the, what happens to this factor 2 in a general D? Is it D dependent or?
I think it will be D dependent, yes.
Okay.
I mean, this case, this will in general be D dependent.
Okay, but you guys have worked out the general D, or you think?
I think I had worked out at some point, but I can show. I can probably tell you. I don't have the result with me at the moment.
Okay, but this phenomenon that you describe in this slide, that
yes,
that there's a particular trajectory and so on and so forth, that is also true in general D?
Yes, yes. And actually the argument for that was provided by Richard Davison. And this is nothing but the first law of thermodynamics. And this will be true in all dimensions, that for the charge diffusion mode, you have to keep track of the T dependence carefully. It happens because of this, because of the first law of thermodynamics, TdS equals mu d rho, and therefore TdS minus mu d rho, and therefore when you want to when you take the T going to 0 limit, your d rho vanishes, and therefore when the charge diffusion mode is sort of frozen, and that obviously works out for any dimensions, because the first law of thermodynamics will be true in any arbitrary spacetime dimensions.
Okay, but
is it okay? So if there are no further questions regarding this point, let me briefly mention a key feature of near-extremal fluid dynamics, and where we cast the problem of fluid mechanics as an initial value problem. So it turns out that it is harder to predict, harder to make predictions in this case. The time derivatives of the fluid parameters cannot all be known to order epsilon square, even when the constitutive relations are known to order epsilon. And this happens because of this relation. So this is the time derivative of the various fluid parameters written in a matrix form, which are nothing but the stress tensor and current conservation equations, 3 from the stress tensor and 1 from the current conservation. And this B1, B2, B3, B4, they are quote unquote the right hand side of these equations, which involve spatial derivatives of the various fields. And we can invert this matrix and take it to this side to see what our time derivatives are. However, it turns out that the determinant of this matrix is of order the temperature. And therefore, the inverse is order temperature inverse, which makes the inverse very large. It turns out that the time derivatives of only 3 of the 4 parameters can be computed to order epsilon square. This is the time derivative of the beta I dot and a particular linear combination 2 mu dot plus square root 3 t dot. And the time evolution of the one parameter that remains, that's not a linear combination of these 3 parameters, that can be computed at most to order epsilon square over t, which is what I was saying in the previous slide. So what does this mean? This means that the system heats up and we are out of our regime of cold fluid mechanics at a time scale which is much shorter, which is shorter by a factor of t tilde. Remember that our equilibration time scale is given by mu inverse. So this system over here heats up much more quickly than expected at a time scale of t tilde over mu. So this is, I think, another good point, and I'm just coming to the last part of my talk, and I'm nearly at the end. So is there any other question that you think I should address?
Well, about the system heating up, like there will be perturbations which keep the system extremal. There is a class of perturbations which keep you close to extremality.
Yeah.
But the way you have presented, it seems like all of them lead to heating up of the system. So no, that cannot be.
No, what I mean is that this beta I dot, I mean, when you just estimate the time scale, let's say where the beta values or the temperature values change drastically, the time scale of heat, I mean, there's obviously some heating up going on in all the cases, but what I'm saying is that the time scale of heating up is smaller than in conventional fluid mechanics, because in conventional fluid mechanics having a 1 over t is not a big deal, because epsilon itself is much smaller compared to the scale set by t. Is that okay?
Yeah. So sorry,
yeah,
can I?
Yeah,
Oh,
sure.
No. I think Spenta had a question. Please go ahead.
Yeah, I'm getting a little bit lost in the sense of the consistency of the final result, because in fluid dynamics you expect local thermodynamic equilibrium to hold, and there seems to be, unless I'm missing something, some problem with that, right?
Well, no, we still expect, okay, what we are saying is that obviously this local thermodynamic equilibrium will hold, but compared to what scale? I mean, we are putting a bound on that scale. So in conventional fluid mechanics, the local thermodynamic equilibrium will hold in a scale of mu inverse, which is the scale set by the chemical potential. here also, obviously, the the basic statement is that it will hold, but it holds for a shorter time than one would naively expect.
So does it mean that the fluid dynamics equations actually cannot be integrated over long times? Or?
Yes.
Yeah.
I see.
Indeed.
Yeah. Sorry, can I just say something, Upamanyu, if you'll permit?
Please go ahead, sir.
Yeah. So, Spenta, yeah, as you were saying, you know, somehow, so we were trying to do a perturbation theory in temperature, you know, over omega, and then omega much smaller than mu, etc. And
Yes.
that entire perturbation theory breaks down because temperature becomes of order the frequency after some time scale.
Yes.
After that, you know, you enter a regime where there isn't an obvious small parameter because temperature and frequency are of the same order. But actually, and this is something which Shiraz also emphasized to us, thereafter you might think, because the system is heating up, that it will then enter a regime where the temperature is bigger than the frequency. So you might then hope to again enter a regime where you have a small parameter, namely the momenta are all much smaller than the chemical potential. The temperature is much smaller than the momenta and the chemical potential, but the frequency is the smaller scale in some sense.
Yes.
And there we may get a new kind of fluid mechanics, actually. So that we are trying to investigate. But the regime we looked at least we depart from, because we did an ultra cold limit, and the system heats up from that ultra cold.
Right. Thank you.
But within the class of this ultra cold fluid dynamics, there are genuine perturbations. There are genuine perturbations which keep the system ultra cold.
Yeah, that's, I think, a good point. Upamanyu, if you go back to your 4x4 matrix,
yes.
Now, I can't do it in my head. We'd looked at it a little bit. What Amitav was saying is, aren't there linearized perturbations which keep T dot small or even zero in some sense? You know, where you're not producing, or does that not happen?
I think that cannot happen because of the non-linearities, because there's some order epsilon square would always be there, and generically it's I mean it's very small, so it happens over a long time scale, the heating up or the change of the fluid parameters. But I think as long as we are in non-linear regime, I think it will have to heat up.
No,
Okay.
may I comment?
Yeah, sure.
So you know, like, I think, you know, like, so you're saying there is 3 parameters, right?
Yeah.
There are 3 directions where, you know, like at least 2 order epsilon it's small. So I think the one thing you can do is that, and these 3 parameters I think can be just thought of as giving, you know, like this extremal, you know, near extremal black hole rotation, or just, you know, like giving changing the mass of the black hole but keeping it near extremal. So those are the parameters, right?
Yeah,
like,
yeah.
You can give rotations along some I directions, or
Yes.
you can in and give it a slight boost, and or, you know, like you can kind of. So now if you think about it that way, it is clear that there are like genuinely extremal solutions, right? I mean, you can just even to any order, right? Because there are like rotating Kerr-Newman.
Yes, yeah, okay, yeah. I mean, there are certain spaces in which it's genuinely extremal. I mean, it's obvious from this beta I direction where you generate some boosts, but it still remains extremal. Yes, that's indeed.
So I think, you know, like, so there are directions. There are in particular there are like this idea. There is a boost and just increasing the mass, keeping and increasing the chemical potential in such a way that
Yes.
That it stays extremal.
Yes. Yes.
So these directions, you have, we know that there are a class of solutions which are exact in Einstein, which are just exact solutions, exact solutions of Einstein equations. So those perturbations should satisfy what Amitabh has been saying, that they should not heat up the black hole if you perturb it in those ways. Maybe that's the point. Yeah.
Yeah. Thank you for your comments.
Yeah, that's right. If of course, if you have viscosity and so on at play, just to sort of paraphrase Loga again, of course, Loga has said it, if you have viscosity and so on, differential velocities, you will generate friction. But, you can have the analog of rigid motion or something and keep those dissipative effects to be either zero or very small, right? Loga, I think this is sort of what you were saying, right?
Yeah, or just perturb it. So let the viscosity do its job. Let things, basically, that's like turning on some quasi-normal modes. But the point is that you're doing it in such a way that you're within the extremal regime. Yeah, extremal, Kerr-Newman.
So does it mean, Loga, does it mean that from the beginning one has to look at the most general solution, which is the Kerr-Newman type of solution? Or
you can look at the general solution, but it's Kerr-Newman with a very small angle.
That's what I'm saying, that you need to begin with non-zero parameters for those directions. That's what you're saying, right? If you did that, then you would. If you did that, then you would not be going out of the near-extremal limit by these equations. Sorry, I mean, maybe I'm confused. Sandeep, you want to say something?
So I think the statement is that there are, generic perturbations do take you out of this limit. If you just throw some general thing into the black hole.
Yeah, that's right. Yes.
It will take you out. So the general perturbation, that's a general story. A generic story is that, is what Upamanyu is saying in this slide, that you just go out. Okay. And then you have to just see what happens and so on. But I'm saying just, I think this is what Amitabh was also saying, that if you kind of don't look at the generic perturbations, but look at some subclass of perturbations, there, you can get some nice story, and those are probably just perturbations.
You have to be very finely tuned.
Yeah, you have to finely tune it. But it's really a tuning only in one direction. In some sense, basically, you have to keep yourself within the extremal loci in the set of parameters.
Exactly. Keep T dot to be either zero or very small.
Yeah. That's right. Yeah, and it's possible to do that along those directions. That's what you're saying.
Yeah.
Thanks.
I also think it should be, I can't now recall whether we did it, but Upamanyu, let's check again. It's just that 4x4 matrix and, putting this constraint.
Yeah.
It should be, I also think, possible, but okay.
Yeah, I mean, all the B, they are all in our paper, all the right-hand sides and so on, and we can easily, I think, see how to achieve that.
Yes.
So, okay. So how much time do I think I'm over by half an hour. So should I go on, or I mean, it's a very little is left.
I think you can go on.
Okay, I'll not take much time, I promise.
Yeah.
Thank you.
Wrap up. Don't patience.
Yeah.
You've been very kind.
Yeah. It's always shorter during rehearsals than during the actual talk. So
it depends who is in the audience,
No, I mean, I'm really glad that I got the audience that I got today, and it's really fascinating. Hydrostatics is an interesting thing to study with a spatially varying forcing function, and this is related to the attractor mechanism in relativity, which many of you know very well about. So just to say that we are interested in this is sort of closely tied to the previous discussion, where we are interested in keeping the extremal horizon fixed, and we are interested in perturbations which keep the horizon fixed, which are time independent. And these are deformations of UV CFT, which are irrelevant in the deep IR. And we perform our metric perturbations like this, and we obtain the metric and gauge field perturbations to order k square in the derivative expansion, and we demand that all the perturbations die away near the horizon, and it's possible to do so. So near the horizon, all the metric and gauge field components show a scaling behavior, and the perturbations decouple into two sectors with the metric perturbation being HYX, the gauge field AY, HYV, and so on. And this is a characteristic scaling exponent, which depends on the momentum and the chemical potential. And the allowed value for delta, for which the perturbations decay on the horizon and which cannot be obtained by a coordinate transformation, is given by this particular value of delta. There are other values of delta, but they are not physically interesting. And this is just 1 plus kx square over 9 Rx square, which is some kx k over mu square quantity. And what we do is we match this near horizon solution with the outside solution and continue it outward, and we match them near R equals RB and continue them outward and see what the behavior is near the asymptotic infinity. And we do find some non-normalizable components turned on here, which means that there are non-trivial metric components turned on the boundary manifold and non-trivial gauge field components. And we found two classes of solutions. And the first of the two sectors, or the two classes of solutions, is a stationary gravitational solution, but not static. Let me remind you the difference between stationary and static. Stationary, the curved black hole is a stationary, which but not static, meaning that all the components are time dependent, but there's no time reflection symmetry. And just solving this, we get the boundary geometry of this form, where this eta mu nu, that's the flat boundary manifold. And we get a slight perturbation involving this, and which is also dependent on the k square. And there's a magnetic field turned on. And it turns out in this sector, the stress tensor and current are separately conserved. And finally, there's also something called static sector. Yeah.
Sorry, what was this xi again?
Oh, yeah, sorry. This xi is a numerical constant here. Its its value is something like 26.
Okay.
And with that same value of xi, we get another class of solution where the fluid lives in a boundary geometry described by this metric. And here the dual gravitational solution is a describes a static space-time. And on the boundary, there's an electric field turned on. In this case, the stress tensor is not conserved separately, but it satisfies this equation, this conservation equation, where this is with respect to the boundary metric, and this F is the electric field turned on the boundary. And let me emphasize again that none of these two solutions are trivial. They cannot be obtained as a gauge transformation of some flat metric or some flat gauge field by some coordinate or even some conformal transformation. So this is all about the time independent solutions. So here I hope, yeah, sorry.
So I just want to understand. So these solutions are not obtained by expanding in kx.
Yes, they are obtained by expanding in k. So let me just, because I had to go over it quickly. So here's the strategy of the actual computation. So, I mean, I will set, let's say you set some arbitrary k, you get this value of deltas, which is 1 plus kx square over 9Rs square. And all your metric and gauge field components, near horizon have this behavior. And in the boundary of the asymptotic ADS2 region, you can expand this function in powers of k. You can expand the exponent here in powers of k. Then you get an expansion near the ADS2 boundary as a power series in k. And now you just solve the all the Einstein and Maxwell equations outside RB, and you match order by order in K. You obtain a solution, you construct the solution outside, which matches with the solution on the inside, near the boundary. And then you take the solution outward right up to asymptotic infinity and see what the behavior is. You find out the non-normalizable component, you find out the stress tensor and so on. You can construct the manifold the fluid lives on, as well as the constitutive relations. And then you can simply check whether they satisfy the equations of motion or not, and which obviously they will. And I'm just describing here the nature of the solution of the fluids on the asymptotic boundary.
So this, so just to confirm, so all these expressions are accurate up to order kx squares?
Precisely, yes.
Okay. Mm-hmm.
So up to kx square, I mean, this is a solution of the Einstein equations as well, that it's a up to order k square.
Yeah, so the more precisely, the metric perturbation and the gauge field perturbation, the Fourier transform are expanded up to order kx square. Is that
precisely? Yes.
Okay. Mm-hmm.
So these are the two classes of solutions that we found within linearized perturbations theory up to order k square. And so here are my conclusions. I'm at the end of my talk, and the main takeaway is that this is systematic perturbative expansion even when the temperature is the smallest scale in the problem. Beyond first order in derivatives, the constitutive relations are non-local in time. The analogs of the hydrodynamic modes give the same dispersion relation as the zero temperature limit of conventional fluid mechanics. And I think it's interesting what all of you have mentioned, and this is certainly worth investigating more closely. The fluid hits up pretty quickly, as in it hits up more quickly than one would expect. And there are interesting time-independent solutions to Einstein equations. Oh God, there's some line missing here. I'm sorry about this, which are dual to forced fluid dynamics. And there are lots of interesting things to be done. So that is the end of my talk. And I'd like to thank you all for your wonderful questions and for your attention. Thank you very much.
Let's thank Upamanyu for that great talk.
Thank you.
If anyone has any questions, you can ask.
Yeah, Upamanyu, I have one.
Yeah.
I'm sorry, I'm a little confused actually about the. So, I mean, confused in the sense that you start with an extremal black hole, and then you turn on a perturbation, stuff starts falling in, and clearly you go away from extremality, and but there is a regime which can be systematically investigated for a certain short time, during which the fluid dynamics equations are correct. Is that the punchline, really?
Yes, yes.
Okay,
indeed.
all right. I just wanted to understand. Just, I mean, I'm a little bit rusty on all this, so.
That's impossible for me to believe.
No.
Yeah, and sorry, Spender, just to say, there is some short time, yes, when these equations are valid. And what we've done is obtain the equations which you could use in that period when the temperature is low enough. And then it turns out, actually, sorry, just to repeat in this long talk, that in fact the systematic derivative corrections are non-local, but luckily small. So you can get away in this period with just the leading corrections, which include viscosity and so on. which are local. So
yes,
at least it's not as bad as the situation might have been, you know?
yeah. No,
That's
no,
all.
that's,
All right.
yeah,
Sorry.
thank you. Thank you.
Thank you.
Very interesting.
Thank you.
Are there any more questions?
Yeah, so I had a question.
Yeah.
Which is about, you know, like these log omega pieces.
Yes.
So when you come to this fluid dynamical description, let us say I kind of allow my viscosity, my eta, and the diffusion constant and so on, which appears in the current. You know, like let me talk everything in the Fourier domain so that that it's easier. So that's of course, you know, like a constant in Fourier domain to start with, right? You know, like if you just viscosity, but I can think of some kind of frequency dependence in viscosity, and I can add some omega log omega terms to that. Okay. So my question is this: that your various log omega things that you get at the next order, can they be just thought of as corrections to the viscosity and diffusion constant, the AC viscosity and the AC diffusion constant, corrections which go like omega log omega, which are small, I agree, but you know, but can they be just absorbed into that? Or is there a piece which cannot be absorbed into that when you calculate the stress tensor and current?
Oh, this I'm not. Could you please repeat? I mean, in brief, your question once more. I'm sorry. Whether you want to know whether the non-analytic pieces in the constitutive relations can be absorbed into the various fluid
can be
parameters.
Just absorbed into some non-analyticity of eta and diffusion constants. And nothing else.
Well, I think I don't think that will be completely correct, because what will happen is that I'm not sure. I'll have to check this once for myself again. But what I think will happen is that for them to be called the corrections of the viscosity or the various transport coefficient, the accompanying piece has to be the same. Namely, we are calling the coefficient of our sigma mu nu the viscosity. And I don't think it's obvious that all the corrections will be of that form when we evaluate them. So I don't think they can be simply, sorry, go on.
Yeah, sorry, maybe let me just make more precise. I'm not saying all the corrections will be of that form, but I'm saying all the non-analytic corrections will be of that form. There'll obviously be some things like omega square and so on and so forth, and that will lead to like some second order constitutive relations. But I'm asking whether, you know, like the non-analytic pieces, can they be understood as, you know, like just corrections to the viscosity and so on?
I think even the non-analytic pieces will involve some of these additional derivatives. So, I mean, it's not obvious to me that they can be absorbed into viscosity, I mean, at the moment, but I think it will be a nice check to do.
Okay. So just, you know, like, I mean, one comment, which is that, let's say, you know, if you do like 1 by n corrections, which is like, if, you know, even in ordinary fluid gravity, if you do like 1 by n corrections, which is that you start considering loops in the bulk. Okay, which show up as 1 by n corrections in the CFT. Then it is expected that, you know, like you would get pieces of the type you're saying, where you have some power of omega log omega correction. For example, you'll get it in the viscosity. So these are what I call the long time tails and so on. So these, but usually we don't worry about them in fluid gravity because they are kind of 1 by n suppressed. Okay. And what I was trying to understand is that you're just saying that now there are long time tails, but they're not like, they're no more 1 by n suppressed, but they are kind of there in this extremal system. Their long time tails are not 1 by n suppressed. I was wondering whether that is the possible interpretation. Yeah, so that's why I wanted to understand, whether there is whether this omega log omega piece, whether it just shows up in the viscosity, in which case it would be like the standard long time tails.
That's a great point indeed. I think we'll definitely look into it. And at least in the context of this paper, we didn't think of it in terms of the 1/n corrections, but I think that's a great point that you bring out, and I'm sure we'll be discussing it.
Wait. I think, Loga, let's say we are at zero temperature just for a moment, then the first time the log omega comes is actually at the 2 derivative level. Upamanyu, you can correct me, it's with omega square that we get the log omega, right?
Right.
But anyway, if we were to include 2 derivative terms, let's say, then in a sense, the coefficient would acquire a logarithmic correction.
Yes. So the real question is about the tensor structure, whether, like the first order tensor structure is enough to absorb the non-analyticity at the second order.
No, because the expansion is every power of log omega comes with a power of omega. Or yes. let me back up. At least the first time the log omega comes is with omega square. And isn't that how it goes? It's omega to the n log omega to the n minus 1, right?
Exactly, yes.
Yeah, sorry, Loga. So that's how it goes. Sorry.
So Sandeep, the question is what is the coefficient of that? What is the tensor structure? Is it like omega square log omega sigma mu nu? For example, let's say I compute T mu nu. Okay.
Achha.
The question I'm asking is that omega square log omega, is it like omega square log, is it like omega log omega sigma mu nu? Sigma mu nu is already like omega.
Oh, I see. That's what you're asking. Okay, I didn't understand.
Or is it something else? Yeah. Okay.
Yeah, I mean, I think that's a great point, and this is I think what I think we should look into. And it might be that the tensor structures are the same that are involved with the viscosity. But I can say at the moment.
For example, that would explain why you get omega square, why log omega can appear with only omega square, right? Because if only the omega log omega came only with eta, let's say, then, the first log omega will be omega square log omega. Okay. So if,
No, go on. I think you're probably right, but I'll say, but you go on and just complete, Loga. Go ahead.
Yeah. So that's the thing. The point is that, it's a long time tail which shows up in the viscosity. Okay. And then, that would kind of, if that is the physics that is happening, okay, that whatever is, now if that is what is happening, we kind of understand at least in the standard fluid dynamics what omega log omega terms contributing to the viscosity is. It just the long time tail. There's some general story of how like the fluctuation don't die out, and they have some power loss in the. So when you calculate the Kubo viscosity, you get some omega log omega terms. Which kind of which causes some effect. So then like one would be able to apply that theory and understanding to what is happening, and it would explain also the powers that you're seeing, why order epsilon it works, and why order epsilon square is the log omega and so on. But for this picture to be valid, one needs to check that it can be absorbed into diffusion and eta. The second order omega.
Let me try to understand what you're saying. But first, Loga, I think it's almost clear to me, Upamanyu can say, but it's almost clear to me that it's only in the spin 2 channel. And, that's the channel which maps to this minimally coupled scalar. And in the other channels, I think, Upamanyu, we were much better off vis-a-vis any log corrections. In fact, I don't think we were getting them at all.
I mean, we'll eventually get them at sufficiently high orders.
Oh, maybe you're right. At high orders, they sort of feed in, right?
Yeah, because they will all have to, I mean, because everything couples to everything at sufficiently high orders.
But there's a sort of sense in which the leading log violations are only in the spin 2
yes,
channel.
That's right. That's indeed right. And I think I mean, I think what Loga is saying actually does make sense, because I remember that, I mean, if we do, I mean, in linearized perturbations, if we just do the one higher order calculation, I think the effect there will be kx omega log omega, which suggests that it's actually renormal. I mean, just modifying what eta is. I think what he's saying sounds right. But
Yeah.
I have to go.
Now, yeah, we'll check this very interesting comment, Loga. In some leading sort of sense, I think it's correct, if not entirely. But tell me this, what is the story you say we can connect this to? I don't know this about log violations in viscosity.
Yeah, so these are, yeah, these are these are what are called long time tails. And we also know that they are there when you calculate 1/n. I think this was worked out by Karan Huat and Saremi about 10 years ago.
I
you
see.
can search for long time tails in ADS or something like that, you know, like
I see.
I think that was there. So but the fluid dynamic story itself is known for many decades, that there are, if in large and kind of situations, there are 1/n corrections to these things, to things like viscosity, which go like 1 by some power of n omega log omega things, you know. So
okay, we didn't know this. We didn't know this. We'll bug you for, you gave some references, but we'll bug you for more general and see. Okay, very, very good. Very good. Thank you. Thank you.
These are due to fluctuations in some sense. Basically, you know, like there's a, you know, hydro is a kind of, is just a mean field theory kind of thing.
Yeah.
Strictly speaking, you have to take into account fluctuations of the hydrodynamic modes.
I see. I see.
Let the hydrodynamic modes run in loops in the effective theory. If you think of hydrodynamics as an effective theory.
I see.
And the loops of these hydrodynamic modes actually lead to these terms.
Oh,
and because they are loops, they are 1/n suppressed in the hydrodynamic side. And they are like, they are loops in the gravity side, basically.
I see.
Basically, you let the quasi-normal, long-lived quasi-normal modes run in loops in the bulk. That gives rise to
and maybe the long-lived or whatever, the fact that the pole is coming down to 0 gives you the log, is it? Or something like that?
Yeah, something like that, yeah. So I think the statement here is perhaps the statement that here the long time tails are not so suppressed, but they are,
yeah, that's certainly true. That's certainly true. They're sort of log enhanced in a sense. Yeah. Okay, thank you for that.
Yeah, so just one more question and then I'll shut up. So have you guys looked at, you know, like whether something similar happens with extremal care?
Well, yeah, no, I think that's a great question, and we haven't looked at it. Upamanyu, you're not been looking at it, sorry. But we expect something similar. But what do you think? I mean, momenta will become rotation, as you were saying, but we do have a near horizon ADS2. I don't think Upamanyu mentioned this, but one of our motivations was to map, you know, when we split the problem up into the inner region and the outer, our motivation was to map the dynamics of the inner region to JT gravity. And well, we haven't quite developed that, but for thermodynamics, we did show that the near-extremal curve inner geometry correctly reproduces, maps to JT and then correctly reproduces thermodynamics. So anyway, bit of a tangent, but I think there should be a story for near-extreme curve, but we haven't done it yet. Do you have any thoughts or comments on that, Loga?
No, nothing useful, I think. Yeah, okay, anyway.
No, but you know, I think it's actually the reason I'm so keen that Upamanyu do this is that it's physically the most interesting, right? Because you may hope that the isometries of the ADS2 help you, and you can say something about near-extreme curve in the sky. And, you know, there was all this work of Strominger, etc., on trying to do this kind of a thing. But I think they didn't quite get it right because they missed the fact that, which we now know in JT gravity, that it's not ADS2, it's ADS2 which is broken because of the rolling dilaton or whatever. But with that put in properly, there should be a very beautiful, nice story, which connects to what Upamanyu was describing. But okay, we didn't do it yet, sorry. But if you have any comments or thoughts about that, we'd love to hear about them from you. Yeah.
Okay. Yeah, I don't have anything particular to say now. Okay, anyway, thanks.
Okay.
So may I ask something, if you don't mind? Sorry about that. I mean, so I'm just trying to understand. So, so I mean, hydrodynamics is basically something you write down based on symmetries with unknown coefficients, which your dynamics has to somehow calculate. So now you have what your calculation and what Loga is saying is all consistent with that, but these coefficients actually turn out to be a little bit more subtle to compute if you are near extremal, and you have to take into account the loops, so you get 1 upon n square suppression. So Loga, is it true that the suppression always has this type of factor, omega log omega?
Yeah. So basically, you know, these are long time tails. So they kind of, you know, they kind of don't affect the long time behavior, but they correct it by power loss.
Power loss.
Hence,
okay. So
hence the name. So they're kind of tails. It's true that the system. So basically, when you have a conserved quantity relaxing, okay. So you would expect that, you know, like it relaxes like diffusion, okay.
Yes.
That diffusively, but the point is that that doesn't quite happen, because once you take into account fluctuations, you get like, which are 1 by n suppressed, Avogadro suppressed or whatever, you know, like, and then, you know, like what you get is that this diffusive decay is corrected by, you know, like some long time power loss.
Power
okay.
law. Okay.
So that's a usual thing. I do not know what is happening here. Here there seems to be some long time tail, but it is not suppressed Avogadro wise. Maybe because the fluid is interacting with some other, you know, like a low-lying mode, which is then running into loop and then correcting the viscosity. So there's some fluctuation, but it's a bit like near the critical point. The fluctuations are pretty huge, and they're kind of not Avogadro suppressed. They're not like as suppressed as you would think. Somehow they are enhanced because there's some low-lying mode or something which is running in loop.
That's yeah. Sorry, please go on. Please go on.
Yeah, I don't know whether that's what is happening. You know, for example, this kind of behavior will happen when you have a fluid and you couple it to some Goldstone mode, right? And then you let the Goldstone mode run in loops. So that will not be like 1 by n suppressed. And then you might get some something like that.
Yeah. So actually, I don't think Upamanyu said this, but Loga, I think the story is connected to what you're saying, because, you know, if we take let's go to the extremal limit first by being at some temperature T, which could be small, but let's turn it on. Now, as you know, of course, you have the hydrodynamic modes with their poles exactly at 0, you know, where omega goes like k square. So as k goes to 0, they come down to omega going to 0. But then you have the higher quasi-normal modes, which are gapped by the temperature, right? Now, what happens in the extremal limit is that all these quasi-normal modes coalesce at the origin. And that is why you get the log branch cut.
Yeah.
You know, if you heat it up, then the log branch cut goes away, but you have these very closely spaced quasi-normal modes. And so, you know, a little bit the system deals with them, but by generating this log cut. And the only thing we have to say is that despite the log and so on, you know, you do have a systematic expansion in that the logs are coming with extra powers of omega, you know. So you don't have to throw the whole expansion out. But that's I think that along the lines of what you're saying, it's that accumulation of the quasi-normal modes which is giving this kind of a log in this system.
Right. That doesn't happen in the usual thermodynamics, actually, in the usual non-extremal case, because they just this is okay. Good point. I understand.
Yeah. No, just to ask Loga about the fluid dynamics, 1 over n correction that he was mentioning earlier. I mean, it's some sort of off-shell fluid dynamics, right? What you're describing.
Right. There are fluctuations. It's a fluctuating fluid dynamics, as it's called, fluctuating hydrodynamics. Yeah. It's off-shell. Well, yeah, in some sense, but it's basically you add fluctuations to the hydrodynamics, and then you have to do some stochastic integral over them.
Right. So
yeah, I can say it's like off-shell.
It's a very hot subject in statistical mechanics.
Is that right? I see.
Yeah, adding fluctuations, noise terms to all these hydrodynamic equations and calculating.
Yeah. I was just wondering that whether what is being described is just, like you take fluid dynamics and then you couple it to some Schwarzian mode, which gives you the noise, which you integrate out and you get some long time tails, or whether that's the physics that is going on here or something like that.
To a Schwarzian mode, right? You're saying?
Yeah. The Schwarzian loop contribution to some, so there are like the usual hydrodynamic modes.
Yeah.
So this is some kind of like a two fluid kind of picture, like what we do in superfluid, where you have a Schwarzian mode and then you have hydrodynamic modes, and there's some coupling. Let's say there's some 3-point function where a fluid mode goes to two Schwarzian modes or something. And then you kind of make a Schwarzian loop, which then corrects the fluid viscosity by some omega, log omega, and things like that. But some sort of that kind of picture would tell you what is happening in the CFD. Because
no, I think this is another very good point. As I said to you, our original motivation was that we would like to understand it in terms of the JT gravity living on the boundary. As you know, Upamanyu had a boundary he created where the ADS2 throat joins to the far region. And what we really wanted was to replace the entire inner dynamics with JT gravity. In other words, some kind of a Schwarzian theory, and couple that to the outside fluid to get the entire result. But just the direct analysis was subtle enough that we got kind of tired and we didn't then match to this picture. But I agree with you, there should be such a picture. And actually that would be the most universal way to describe it, because JT gravity universally arises as the near horizon limit of extremal systems, whether they occur as we were saying, or charged or whatever. And if we can recast everything like that, then it becomes the universal description of near-extremal black hole fluid mechanics. So I think what you say, I mean, it's clearly the right thing to think about, but I'm very sorry to say we sort of flaked out after getting this and we didn't connect it. That was the original motivation, but we sort of lost steam. But I agree with you, something like that would be very good to try and understand. It should be what happens, but I don't have anything more to say, sorry. Upamanyu, you have been relaxing too much now. This paper came out many months ago. See, look at all the questions.
No, sir, not relaxing. There are too many things on the plate.
Okay.
Not to mention a good dose of corona in all our lives.
No, thank you. Thank you for that comment also. It's very, very, very important comment, Loga.
Okay, if there are no more questions, we can thank Upamanyu again. And let's conclude.
Thank you very much.
Okay, see you guys next time.
Bye.
Bye.
Bye. Bye.
Thank you. Thank you, everyone, very much.
Thanks.
Thank
Thanks
you.
for